Good evening and happy Thanksgiving, if you celebrate Thanksgiving. My name is Drew Desker. I'm the director of Kopernik Observatory. And it's great to have a whole bunch of new faces here, actually. It's great also, obviously, to have our return visitors, but hello. Thank you for coming up here. Where do I start? Well, anyway, again, for those of you, actually, who's here for the first time? Wow, a lot of people. Okay, actually, hold on. We've also got our live stream going on here, so everybody who's here for the first time, raise your hand and wave to the people on the live stream. All right. Now, for the people who've been here before, wave your hands. All right. Excellent. Nice mix tonight. So, for those of you who are here for the first time, just a little story about a little background about Kopernik. Back in the early 1970s, there was a group of Polish immigrants, people of Polish heritage, that wanted to commemorate Kopernik's 500th birthday. We know him as Nicholas Copernicus, but his Polish name is Mikołaj Kopernik. Does anybody remember what Copernicus was famous for? That's usually the response. Okay. He developed what's called the heliocentric model of our solar system. 1973, Kopernik would have been 500 years old, and so rather than buy a statue, plunk it in the parks, they said, let's do something. So they built the original observatory, which is actually, the building that they built was actually, there were two buildings. This brick wall is one of them, and two of our three domes were part of that originally. It was then donated to Roberson. And in the 1990s, they expanded it to where we are today. In 2007, Kopernik came back to the Kopernik Society, that group of Polish immigrants who wanted to commemorate Kopernik's birthday. And Kopernik Society has been running this facility as a public observatory and informal STEM education facility. We do a wide range of things. So every Friday night, like we're doing tonight, from March to mid-December, we always do some sort of a public program. It isn't always about astronomy. Let's see here. A couple weeks ago, we had two meteorologists from the National Weather Service talking about that big snowstorm we got back in 2020, where they dumped like 40 inches of snow here, and then you go like 50 miles east or 50 miles west, and they only got like 3 or 4 inches. So we do a wide range of topics on our Friday nights, but we also, again, being a STEM education center, we do a lot of work with students of all ages. We have a program called Kopernik Kids for kids from 3 to 6 years old. We go to schools, or schools come here, and we'll do programs. You go to our website here that Roy is driving here, and it gives you a nice list of what we have coming up. So, as I said, tonight's program is Black Holes on Black Friday. Next Tuesday is Giving Tuesday. So we actually are also in the middle of our year-end donation. Some of you may have already received letters from us about it, but we are a nonprofit. We are not affiliated with any university, or all the funding we get is literally from people just like you. And so if you're in a position to help us out, we would love to have your support that way. One of the things that we did back in 2020, we were doing our Friday night programs, and then COVID hit, and he said, "Okay, well, we have to close down. So we'll shut down for a couple of weeks until this thing blows over." And here we are still. But when it got to be about May, we decided, look, this is not going to blow over anytime soon. So we started to live stream. We still had our presenters lined up, but we had them do is we had them zoom into our facility here. We then turned that back around and put it out on our YouTube channel. Our YouTube channel now has nearly 13,000 subscribers. We've beyond our Friday night programs, we've done a number of other programs. Actually, if you want to go to go to this. Right there. We do, again, our Friday night programs, but also if there is a particular a live observing session opportunity, like back a couple weeks ago, there was a lunar eclipse. Anybody get up at 4 o'clock in the morning to see that? All right, very good. Well, you can actually We did that back in May. There was another lunar eclipse, and on that particular lunar eclipse, I think it started around 10:30, 11 o'clock at night. At one point, we had over 25,000 people watching simultaneously. The chat that was flying by like a CVS receipt. It was extraordinary. The other thing we also do is we call it Kopernik reactions, KRNX, and what we do is we might take if there's a launch of a specific interesting mission like the James Webb Telescope or Artemis, or when a local astronaut Doug Hurley launched on the Falcon rocket on the SpaceX Crew Dragon. We basically had that as an inset, but we also sort of had our own community that was sort of reacting on that. But what's nice about our YouTube channel also is that you can go back to it. So anything that's on our YouTube channel, you can go back to at any time. And actually, what Jeremy does is a nice job. He actually, after pretty much every one of our programs, he'll go and put little chapter marks in there, so you can go specifically to that area that you may want to review again. So let's go back to our website for a second here. So yeah, a couple of things that are coming up. So actually next Friday is going to be an update on the James Webb Telescope and the Artemis mission that's currently still, is it still orbiting the moon? I think it's still orbiting the moon right now, right? Yeah. So we'll talk about that next Friday. But then also on December 7th, there is an event that's going to happen called it's a Mars occultation. Actually, the lunar occultation of Mars. So the moon is going to pass in front of Mars, and provided it's clear, Jeremy will be up here, put a camera on one of our scopes, and you'll be able to watch the occultation specifically from on a YouTube channel. What's also interesting is that there are other observatories that do similar kinds of things, but there was one called the Dortwood Observatory that actually pointed people to us because they won't be where they're located. They won't see that occultation. So it's sort of nice to get that kind of connection. And it's been nice also. We've met a lot of neat people on our live stream. For about 2 years, again, we just couldn't have people up here. But what's also been nice is those people who live locally. When we were finally able to open back up again, I said, "Oh, you're the person I saw on the chat." But also, again, we literally had people from literally around the world. When there was Comet Neowise in 2020, people would chat. I'm in Oslo, Norway. Where do I look for it? I'm in Indonesia. Where do I look for it? So it's been a great opportunity for us to sort of expand our outreach. One of the things that we really try to do here at Kopernik is really, we're not going to turn everybody into an engineer or a scientist, but we are going to try to at least have you walk away with a little more knowledge than you've done in the past. One of the programs we run is called Girl Power Science, and it's an opportunity for girls from 3rd to 8th grade to come up and see other women in that have chosen STEM careers and might learn about that particular career a person has done. We just did one on rockets just about a week ago or so, 2 weeks ago. One of the programs that we did a few years ago we always have a female subject matter expert talk about the work that they do with the girls. They usually zoom in for it, for that. But so this one time we had a NASA astrophysicist talk about the work she does using satellites to look at carbon dioxide levels and how that affects global warming. And then our girls, at the end of her presentation, gets to ask her questions. And one of the girls asked, "How did you get interested in astrophysics?" Now these are 3rd through 8th grade girls. And I loved her answer. She said, "Well, when I was in college, I was an English major, but my boyfriend was a physics major. We would go from observatory to observatory. I eventually dumped the boyfriend, but I kept the astronomy." Now she has her PhD in astrophysics and works at the NASA Goddard Space Flight Center. So you never know where a seed's going to get planted. So I think we've got some fertile ground right here in the chairs here this evening. I'm hoping we might plant a seed. Maybe you guys will be the next ones to know more about, teach us more about what's going on with black holes. So to that end, we are going to transition over to Roy Williams. Roy is one of our educators. and has been here for many, many years. And I don't know if you can fill in other gaps about Kopernik and take it over.
Sure. Okay. Well, thank you, Drew. So it's true. I've worked here many years at Kopernik Observatory. I now teach at Charlotte Valley in Davenport. But what makes me really qualified to do this is I stayed at a Holiday Inn Express last night. So it's still not that old. Okay. I haven't seen those commercials in a while. So, all right. So black holes, monsters of the universe. So in order to get into black holes, we've got to talk a little bit about star formation. And what we have here is the Eagle Nebula. This is a picture from the Hubble Space Telescope. And it's zooming up to the beak of the eagle. And you can see that in certain places it's glowing. And that's because their stars are just turning on. They're starting to spit out ultraviolet light. And it's making the gas actually glow. So it's not really so much reflected light as it's actually glowing in some places. And these little nodules here, like, let me get my cursor there, right about there and right here. These little globules is where the stars are forming. And so in terms of new stars, there's a variety of sizes and colors that stars come in. They go from blue to red through the whole spectrum. All right. And blue stars being extremely hot, red stars being on the cooler side. All right, and typically, though, the more mass, the brighter and the hotter the stars are, and coincidentally, they burn out quicker, though. Even though they're more massive, they run through their fuel that much quicker, and so they actually have shorter lifetimes. These massive stars, the ones that turn into black holes, are very short lifetimes. So more mass actually equals a shorter lifetime. In terms of the very beginning of a star's life, you got the protostar phase. That's when matter is starting to circle around a central gravity point where just by chance matter has collected and it's forming what we call an accretion disk. The contraction of the gas and dust form the central star. In our solar system, our star makes up 99.87% of the mass. So most of the mass of the solar system went into the sun. And keep in mind that it's made of the lightest elements, so hydrogen and helium. So that means it's gigantic, right? So 15 million degrees is when nuclear fusion starts happening. You got electrons are stripped off of their parent atoms, creating a plasma. Plasma is the fourth state of matter. It's closer to you than you think. In these light bulbs up here is a plasma. Electricity is going through those fluorescent lights and energizing it. And so plasma is just a gas that conducts electricity. So, but you got this fight of outward pressure of the gas balancing the inward pressure. Eventually that happens, and that's when you got the stability of the star. But what you got here is releasing a great deal of energy through nuclear fusion, and then you got that stability I just talked about. So, and of course we're all familiar with the equation that governs this. You might not be. I think you all know it, right? So what's the formula that relates energy and mass? Right, E equals mc squared. So we'll talk about that in a little bit. So when is a star a star? What you have is when you have nuclear fusion. So at a certain pressure and temperature, the atoms, 4 hydrogen atoms will form into a helium and also release energy. That's what Einstein's famous equation says. Okay, E equals mc squared. So if you weigh the four hydrogens in the helium, you get a little missing mass, and that missing mass turns into energy, and that's what's going on. So this actually occurs in a 3-step process, and it's known as a proton-proton chain, but we won't go into that. But a forming star is considered to be a true star when nuclear fusion takes place, and it's happening in the core. All right. So here's what's going on. You have 2 different isotopes of hydrogen coming together and fusing into an atom of helium, all right, and releasing a neutron, all right. So, and of course energy in different wavelengths and so forth. So that's what fusion is. So what we have here is that we have the creation of a new element, helium, and then as stars age, larger stars will make the other elements all the way up to iron, and then that's the moment the star is going to start to die, and it will supernova, and then create the other existing elements that we know of. So Everything, so in order for us to live, stars had to die. So we, as Carl Sagan famously said, we're made of stardust, right? So stars had to go through their life cycle in order for carbon and oxygen and things that we're made of. The hydrogen was there. We're mostly made of carbon, hydrogen, and oxygen. That's organic. And so the hydrogen was already there, but the other elements had to be made in stars. So, and again, so this hydrostatic balance is kind of crucial. You got the explosions going outward and the gravity of the mass of the star pulling inward. And most of the time it's balanced. And that's when a star is on a thing called the main sequence. We'll show that in a second in the Hertzsprung-Russell diagram. Here it is. So basically what you have on the HR diagram is you plot the temperature versus how bright the star is intrinsically. In this case, they're doing it in how bright it is compared to the sun. You have one sun, you got 10, 100, 1,000, 10,000 suns, okay? So we're comparing it to our own sun. So if you just go straight over here to where it hits the yellow one, that's where that would be our sun on the HR diagram. And this kind of curved line is where most of the stars are going to be for most of their life because of that hydrostatic homeostasis type of thing, where the gravity is equaling the force of the nuclear explosions outward. So it's very stable. So they came up with a spectral class. So 35,000 degrees and higher are O stars. You got B stars. You got A stars. You got F stars. Our star is a G star. We're kind of on the small end. So our star is not going to turn into a black hole. And then you got all the way down to these red stars. All right. So anyway, that's basically a layout of the main sequence. And then we're going to go through this when they turn into red giants, and down here is your white dwarfs. That's going to come up in a little bit too. So layers of the sun, you have all different layers. The Earth is layered, the sun is layered. So that's a common thing you see, a common pattern you see in the universe. The core is where most of the nuclear reactions are occurring. It takes light a long time to get out. I'm forgetting the exact number of years, but it actually takes a long time. What we see through our telescopes here at the observatory is what's called the photosphere, which is actually beneath the chromosphere. But we look at sunspots with our heliostat. When you take the tour, I'm sure we're going to show you the heliostat. And that's a telescope in physics that projects the sun onto the wall and allows us to see these storms on the sun called sunspots. And these are actually cooler areas on the sun, a couple thousand degrees cooler, and they're big. They're going to be at least the size of the Earth and bigger. We are starting to go up in the solar cycle, so it's been boring the last few years, and now it's starting to get more sunspots are appearing on the sun. It's a 11-year cycle. And so that's getting exciting. We do have another filter that allows us to see the chromosphere, and that's where the flares are. So you think of the sun of fire coming out. Well, you won't see that with the white light filter or with the heliostat that we have, but with something called a hydrogen alpha filter, we hook it up onto our telescopes, and we can see the flares coming off the sun. So anyway, that's a quick layout. The last layer is called the corona. And anybody got to see the eclipse, the total eclipse? Anybody traveled a couple of years ago? Okay, where did you go? No, in the hat.
Greenville,
South Carolina. Okay, I was in Tennessee. It was incredible, right? So you got to travel to the next one in Buffalo, or maybe go to Niagara Falls. There'll be like 5 million people there, I bet. But yeah, okay. Yeah, it's going to be a good one. So anyway, that's coming up in 2024. So after millions of billions of years, no hydrogen is left, and then we're going to start powering. We're going to make those other elements. Okay, and they'll start burning helium and creating carbon and so forth. So just to get a comparison of size, you can see the Earth there is a little dot. Our sun. You can fit 100 Earths across the side of the sun. All right. This is a typical red giant, so you can see it's way bigger than our sun. Okay, so again, our sun, when I was in school, grade school, they said the sun was an average star. Now we're kind of saying it's more of a dwarf star. So we got a little more data on the sizes now. and we're seeing that it's more on the small end. So what we're going to talk about today, getting into black holes, is how stars and other objects that are large warp space and time. Okay, so gravity deforms space and time, and this is Einstein's theory. To kind of back up, you had a fellow named Newton come up with the idea of his theory of gravity, and Einstein built on that. So Newton's laws can probably get us to the moon, stuff like that. But to get more precise, Einstein's theory is more precise. So in particular, it explains the orbit of Mercury, the way Mercury would shift around the sun. Wasn't really explained by Newton's laws, but Einstein was able to do that. So space-time, as mentioned by Albert Einstein, is the never-ending fabric of the universe. Fabric bends around objects due to the object's gravity. So what Newton would say is that you could put a ball on a string and you fling around in a circle. That force on the string would be gravity, right? It's pulling on the object as if there's a rope, as if the Earth is held together, as if there's a huge rope going to the sun, and we're being held by that, and there's a force on that rope. What Einstein is saying, and that's why we got our demonstrator over here, our spandex universe, is that it's going to show how curved space really is how gravity works. Okay, or it's a better model for how gravity works. So one of the first things that Einstein said was that if you have a massive amount of gravity, such as a star, that starlight behind the sun, behind our sun, would bend. Okay, that we should be able to see stars just behind the sun, and so because of the curvature. So I'm going to demonstrate that. So we got to be ready to. So I'm going to demonstrate that right now, how that works in terms of. So what we have here is the spandex universe, and this thing is great for showing all types of demonstrations, all types of things. We can just show orbits, just like we talked about. So we got the sun in the center. We got a planet going around, just like this. Okay, I can even take a planet and a moon, and it will circle around that if I get lucky. So there it goes. A little bit. All right. So anyway, what I do want to show you is the concept of what Einstein predicted. And so what he predicted is that here's the starlight. We're actually behind that blue line. We're behind, the star is behind the sun, so we shouldn't see it. However, we do see it as if it's over here, but it's really there. So that white thing is like apparent light path, but that's not really what it's doing. It's over here. So to show you that, I'm the star, and the light's going to go toward the sun, and you're going to watch it bend like that. So did you see that? So watch it again. See that? All right, good catch. There we go. So yeah, so that's the idea. Okay, did that work? Okay. So they had to, of course, this is 1905 is when Newton came up with this theory. Einstein. And so what we got is, you had to go out there and get the proof. And this is why I brought up the eclipse. Because when are you going to see something close to the sun? When it's blocked. And we're the only place in the solar system where a moon blocks the sun perfectly, as if someone did that on purpose as a joke, as if we're in a simulation, and that's the clue. But anyway, right next to it, Arthur Eddington in 1919 was able to observe a solar eclipse, and they were able to, and their instruments and the way they were taking the images, it was just on the edge of being able to do this. So the accuracy of it. And so they were able to pinpoint some stars that shouldn't be there, that are actually behind the sun. Okay, there was an attempt a few years earlier. I'm forgetting the people who did it, but they got. It was during World War I, and so the Germans confiscated their equipment and thought they were spies. But they were released. But anyway, that pulled it off in 1919. Proved Einstein's theory. So what does this really mean? General relativity. So Einstein describes gravity as a deformation of space-time around a massive object. All right, and so you have your usual star, like I just demonstrated, And then something called a neutron star. Okay, we didn't talk about that yet, but it's even a more denser star will pull down that center even more and cause space to get more warped. All right, and this is where we need to talk about the different options here. So what we have is all stars begin in a stellar nebula, in a big cloud of gas. They all start the same way. And there's a predetermined thing that's going to happen in general. There is an exception. I'll talk about that I know of one exception that things can get altered. But basically, you got three routes. And it's all based on mass. Everything about a star's life is predetermined by the mass of that nebula and how it collapses. So if you have a small mass star, you're going to turn into something like we have now, our sun. As our sun dies, it's going to turn into a red giant. It's going to run out of that hydrogen, and it's going to start puffing the outer layers of its skin, so to speak, of its atmosphere away. It's going to swallow up Mercury. It's going to swallow up Venus. It's going to get close to the Earth, and Earth's atmosphere will be gone. And then it will puff away into a planetary nebula, such as like we see in the Ring Nebula or the Dumbbell Nebula. It's called a planetary nebula for an odd reason. Back in the day, probably in the 1700s, the telescopes weren't that good. When they saw these objects, it reminded them of planets, so they called it a planetary nebula. And so that name is kind of stuck there, so it's kind of confusing for us. But a planetary nebula is what you're going to get. And then in the center of that nebula will be a dense star, white dwarf, probably about 20 miles across, something along those lines. That's the end of that. So it'll slowly cool. It's going to be very hot. It's going to be very hot, but very small, so it'll be dim. All right? And, what's that? This is us. This is what's going to happen to us next Tuesday. No. So you're used to all this bad news lately, right? So they believed it. Okay. So no, we're talking about 4 billion years from now. So for the kids, we're like worried. Okay. So then what you have is more massive stars. Like I said, they have shorter lifetimes because they're burning up their fuel quicker. Turn into supergiants. All right. Then they explode, and that's when they create all those heavier elements beyond iron. They create, uranium and all those other things during that explosion. And they leave behind either a neutron star, if it's a medium-sized star, and then if it's about 10 times the mass, I'm seeing different numbers, but something around 10 times the mass of the sun, you can start getting into the black hole range, I think. And so, or you turn into a black hole. So those are your three options here. Now, once in a while, well, probably not once in a while, but sometimes a star can be, a lot of stars are binary stars, so it is possible that if they get close enough, they can suck gas off one star and steal it, like cannibalize it, and they can capture gas that way, and that can kind of change the picture of things. But left alone, it's really, if the star doesn't interact with another star, it's preordained based upon their mass, what they're going to end up. So that's really the outline of what we got going on here. So any questions on the diagram? On this? Yep, go ahead.
The stuff that is surrounding the what's to become the white dwarf star, the planetary nebula, what happens to that?
Well, it just drifts away. It just keeps going out into space, and we can see that. We even have videos now of the Crab Nebula because we've been watching it long enough that you can actually, there's a movie out there, you can probably find it online, where you can see it moving. That's a planetary nebula. Again, a terrible name because it doesn't mean anything about planets. It made sense at the time when these guys were looking through, really simple or terrible telescopes, and they look like, so they do kind of look like planets. There's one called the Ghost of Jupiter, which is, forgetting where that is, but it's a fantastic, I love this thing. It looks like a planet. So Ghost of Jupiter, it looks like Jupiter. So it's a really neat thing. Yeah.
Is there a distinction between these planetary nebulae and more regular nebulae?
Yeah, the nebulas, there's the nebulas that give birth to the stellar nurseries, which like the Orion Nebula and the Eagle Nebula, yeah, so there's a difference. They're forming stars, and then these things have the white dwarf in the middle, and they're expanding out, and it's a dying type of thing, yeah. So one's giving life, so to speak, one's making stars, the other one is dying. So, all right. Yeah, oh, I'm sorry, where? Oh, yeah. Sure.
black hole is exotic?
Is it safe to say it's exotic? Well, yeah, absolutely, because it's really at the cusp of what we understand, absolutely. So because no one's ever been inside a black hole, and the amount of forces and and the amount of gravity is extreme, so it's exotic. They're more prevalent than, now we know that most galaxies have supermassive black holes in the center of them. So there's theories about how galaxies get created, and they have to incorporate black holes in them. So and though they will be the last thing to survive. So as the universe expands, right now it's accelerating, not slowing down. We're actually getting faster and faster, moving apart. And one Google, which is 10 to the 100 million, 10 to the 100th power in years, all the black holes will evaporate, and who knows what. So we're just going to kind of die. This is all depressing, isn't it? But anyway, the point is, though, Roger Penrose, who's probably the main guy on this idea, believes that spontaneously another Big Bang will occur after that. Basically, I mean, long story short, I won't. He says that the ending stage of what he sees as the black holes evaporating is equivalent to the beginning of, yeah. So that I don't quite understand, but he's quite the guy. So. All right, so black holes, we're talking about shrinking down until there's a single point, and that was the biggest problem people had with it. In the 80s, it was very skeptical when I was growing in high school. Black holes were still theoretical. We saw these X-ray sources, Cygnus X1, and rock bands like Rush made songs about it and stuff like that. But it was, it was still theoretical. And then now we're very certain they do exist. I'm not quite sure if the mathematics is right, if it becomes an actual single point or something. But so intense gravitational field. So what are black holes? They're intense gravitational field left when a giant star collapses. All right, they're much larger than the sun. All right, we talked about the life cycle, the different options that it can occur. All that's really important. And gravity becomes so big that it compresses, forming a black hole. So it compresses all the matter to form a black hole. So again, there's that classic diagram. So now let's talk about black holes here. So, here's the planetary nebulas. Now that slide's a little out of, I should have had that earlier. But it shows you the white dwarf here, and then right there. So this is, I think that's the Ring Nebula, but it's a Hubble picture of it maybe. So the problem is the pictures they look so different now. Like the Hubble telescope picture of the Horsehead Nebula, it now looks like a mushroom. So it'd be called the Mushroom Nebula if we named it. But here's some more just to get you the idea. This is this is the Ring Nebula here. I think this is the Ant Nebula. So they come up with these catchy names. This is like the Inquirer magazine. Remember that? The Inquirer said that's the eye of God or something. So anyway, so basically the core of the star is all that remains after the planetary nebula is shed. Okay. So yeah, the core is very hot, about the size of the Earth, and is known as a white dwarf. So white dwarf stars form from a star that has less than 8 solar masses. All right, so now let's get into the black hole. So what we got is something really big. Here's an artist's conception of a black hole, and what's happening here is obviously if it's able to capture everything and not even light can escape, hence the word black hole. How can we see it? Well, some of it is indirect evidence, or it's all indirect evidence, and then you have this accretion disk, this material that's spiraling down into it, and as it's going down that spiral into the black hole, it's interacting with with itself. The matter is energizing and becoming very hot, so it's sending out electromagnetic radiation so that we can detect it. We can see the disk. All right, so we should be able to. So here's a black hole that's devouring a nearby star. So, and then also indicative of what we think of black holes are these jets. So because of the way the gas is ionized and the way it's rotating, it's going to create a magnetic field, and the material nearby the black hole, it's not coming from, it looks like it's coming from inside the black hole, but it's not. It's nearby. It's being shot out nearly at the speed of light. So this stuff is going out. The one at M87, I'm going to show you a picture of that. M87 has a jet that goes out for about 1,000 light years. M87 is a galaxy in Virgo. So indirect evidence is what we're talking about. When we see, so as this stuff is going down into the black hole, it's emitting X-rays. That's why we would see these X-ray sources and theorize that maybe those are black holes. All right, especially if they were orbiting around another star, it'd be more energetic, and you'd see the accretion disk as well as these X-rays. So when a black hole devours a star, it emits radiation that can be detected by X-ray telescopes. So let's see. Some of those telescopes are airborne. You want to get above the atmosphere. Now they're spaceborne. All right. There's our classic diagram here. Let me see what I'm supposed to do here. Yeah, let's do. Yeah. All right. Let's. So I'm going to do a demo. So what we got here is gravitational pull of different size objects. All right. So as the mass increases, so does the pull of gravity. So here you're on an object that you're able to throw the ball up this high, then only this high. So the gravity is getting stronger, and then it's so strong on a black hole that you shoot your flashlight, and the light gets bent and goes into the black hole. So that's kind of like the idea of what we're talking about here. So let me show you the extreme. This right here. So we got our little black hole here. It's our spandex universe, and let's see. We're going to need a volunteer here, and I think you're it. Okay, come on. I heard you met someone recently. Come on down. Yeah, we could do it that way. Yeah. So go ahead and what's your name? Dylan. Just grab this a little bit, just like that. Just like that much. Yeah. Try to make it as small as possible. So, all right, that looks good. Now, so here, take a couple of these. There we go. Now we're gonna actually, Dylan, hold up for a second. Let's just do the regular star. So go ahead and release it. Yeah, you're gonna make the black hole in just a little bit. So now this is a regular star. All right. So grab some marbles. Here we go. Okay. Everyone should have some marbles. Okay. Don't lose the marbles. Okay. Okay. Here you guys. Pat. There you go. Okay, we got them. Okay, here, guys, come on over. Here, pass them back to the other guys. All right, here we go. Now, you all want to go, you want to go the same direction. So let's all go, we're going to go this way. You ready? So go ahead, let them fly. Here we go. See that? Ooh, do you see how they crashed into each other? Wow. No, that's supposed to be the sun. Wow. Now let's look at a black hole situation.
Mine just rolled down.
Here we go. Go ahead, Dylan. Pull it down. Okay. Go ahead. Pull it down. Keep going. How much can you pull it down? Is that good? So that would be your black hole. So you're ready to? We're gonna just here. Grab a whole bunch. We're going to throw them all the matter. We're going to throw the matter in all at once. Wait, save it until you're ready. And we're going to watch that accretion disk. Ready? Here we go. 1, 2, 3, go. See all that? See how they're bumping into each other? You see how they're bumping? So that's going to cause those X-rays. All right? Okay, I think that's enough. We got it. All right, we're good. Thank you, Dylan. Good job. Okay, now, yeah, go ahead and release it. They're not going to... No, okay, we're good. Okay. I thought it was going to bounce up a little bit more than that. All right, thank you, guys. Thanks for the audience participation. Give them a hand. All right. So here's another illustration kind of showing the same idea. So a regular star, light gets away, no problem. A neutron star, it's going to bend it. A black hole is going to bend it all the way back to its surface, so light can never escape. All right. So here's our galaxy. We're located right here, the sun. We're in the Orion arm of of the Milky Way galaxy. If we look towards Sagittarius, we're looking toward the center of the galaxy. If you look this way, we're looking toward Cygnus, the swan. Here's the Cygnus arm. All right. So in the summertime, you can see Sagittarius, and you can see that it's really dense with stars. And we're going to go there now. I think that's next. Yeah. So, yeah. Oh, wait. So we're going to go there in just a second. This is the M87 in Virgo, the galaxy with that jet I talked about. So apparently there's a supermassive black hole in this galaxy. And that's a picture. Now, this is a picture of the center of our galaxy. That's what I was talking about, the Sagittarius. So as you look towards Sagittarius, you can see it's very dense with stars because that's the center of our galaxy. All right? And so I got a little video here. That slide is to remind me to go to the video. And let me see. Here we go. So you're going to actually see this is a real, well, wait, let me go back. This is the real video here. So we're zooming in. They were due almost 20 years. I think it's like 19 years of data where we're looking at the center. We're seeing stars whip around something, okay? They're being pulled in and whipped really fast and then go. So here's kind of to clean it up a little bit to see what you're seeing. And they show the orbits. And you can look in the center and you'll see that's where the black hole is. So you can see these stars whipping around it. So they're not being captured yet by the black hole, but they're being whipped around it. So that's another indirect evidence. So we can figure out, we can actually figure out how massive the black hole is, but based upon all this. Okay, so it's just very easy physics in terms of doing that. So our very well-known physics, I should say. But all right, so that's some really good evidence there. But more recently, in 2017. The Event Horizon Telescope took the first picture of what they say is a black hole. Now, this is an array of radio telescopes all around the world, so it's not like one telescope. And this is we're looking at radio light that's been computerized, so people will say it's fake or something. But it shows, we don't see radio. Our eyes only see the visible light, so we have to substitute visible light in its place. But that's what they got out of it. All right. So it looks like you got a little bit of an accretion disk going in the dark area, I guess, is where the black hole is. So I don't know, some people are really excited about that. But here's more of like an artist's conception of what we got. Okay, so you got the jet two jets coming out on opposite ends. All right, and again, that material is before it falls into the black hole, it's getting shot out because of the magnetic field. And there's some new evidence, I'm forgetting the name of the spacecraft, but they've spotted the spiral nature of this stuff spinning. So they're starting to understand it more. Now the Event Horizon is located inside here, and that's where, there's different ways of looking at it. That's where not even light could escape. But if you have mass, you're further out. You're going to get sucked in a little bit further out. The Event Horizon for your spaceship will be further out than the true event horizon, which is what we're talking about is light. So who cares about light? You care about your spaceship, right? So you don't want to get sucked into one of these things. So the guy Chandra was the mathematician who came up with the formula. And this is what you got. So you got the radius of the event horizon is 2 big G times the mass. Big G is the gravitational constant of the universe. It's one of those about 11 numbers or so, or 17 different numbers or so that we don't understand why it's that, but that's just the way it is, There's a certain fudge factor, and Newton was the first one to use I think he was the first one to find that. But mass is the mass of the galaxy, of the object, and c squared is the speed of light. That's another one of those constants. Okay, 3 times 10 to the 8 meters per second. Or 186,000 miles per second. Speed of light squared. All right, so again, you see that in Einstein's equation as well. So that's kind of interesting. So what would happen if you went to a black hole? Okay, according to Einstein, gravity bends space and time. Okay, once you pass the event horizon, there's no going back. So you'll get stretched and stretched Okay, eventually you get ripped into individual atoms. So your feet are probably going to be closer, right? Most spaceships, your feet are in front. So you get stretched, and then you'll get crushed into, I don't know. So it's not going to be good. Okay, myths. Black holes will spit you out the other side. Nah, we're not seeing that. There was back in the 70s and 80s, they were talking, maybe there's white holes. Do we see matter coming out somewhere else in the universe? Okay. So, no, we're not seeing that. Once you're in, there's no getting out. Maybe we're in a black hole right now. But we would know. Time slows down. So here's the other part of Einstein's theory. That as you get closer to a black hole, your speed, your time is going to slow down relative to another spacecraft, let's say. So, or as you get closer. So here you got 50 seconds might go by, but only 15 seconds goes by for that guy because he's closer to it. Now, we've seen a similar thing. So this is where the space-time, so far we've only been talking, I've said space-time, right? The fabric of space-time. We did the demonstration there with the marbles, right? We really only talked about space. Now we're talking about time. So time is involved in this because it's space-time. Einstein considered time and space to be interwoven, right? A fabric. So you can't have one without the other. So anyway, we saw this with the astronauts going to the moon. We were able to put an atomic clock on at least one of the flights, and you know our time on Earth went a little bit faster than their clock. So they actually slowed down as they went faster. So, but that's pretty much it. I thought I had another slide, but so all right. Any questions? Yeah, what do you got? Oh, yeah, we're gonna. Oh, yeah. Any questions online? What's going on with the? Did we have anybody online? Oh, okay.
We'll start here. There's a
Okay.
question. Raise your hand.
There's a girl right there. It's in the unicorn. She's too shy now. Straight ahead.
Straight ahead.
No. Okay.
Okay. All right.
Okay.
Well, we'll give you a chance to think of put your questions together. I know we've got some on the chat.
A couple of questions from the live chat. VW Blue Sky asks, question, does the black hole continually get larger, or do they just flux back and forth, or just remain the same?
Well, they get more massive. I don't know what the deal is, the size or the radius, but they definitely get more massive. And so what they think eventually happens is something, they will evaporate. When I talked about the end state of the universe, which Roger Penrose, what he thinks is going to happen, and is that the black holes will be the last thing left. Because as the universe expands, space and time is expanding, and things will break down. Like atoms aren't going to work the same way, and they'll just kind of evaporate and disappear. So.
All right, and then Alex asks, what determines the likelihood of a neutron star forming after a supernova as opposed to a black hole?
It says mass. I don't know the numbers off the top of my head, so it's kind of like a middle ground type of thing. So it says mass.
Any questions here in the live audience? Oh, all right, here we go. Give me a second.
A statement first. Didn't Chandrasekhar's equation imply that radius was a function of mass?
Yeah, I mean.
Okay, I'm just right because you didn't really say that. You just said it got heavier.
Yeah. So you got big G, you got mass. So speed of light is a constant. Gravity, big G is a constant. Yeah. So mass is all that matters. So what it implies, I think, is that more massive it gets, the bigger the event horizon is.
Yeah. So if you're squaring the speed of light on the bottom, then m must be really big.
Yeah. Right. That's a good point. Yep.
And then the faster you go, the slower time gets, right?
Yeah, the faster you go, the slower
so
it is
as you approach
relative to another point. It's like in your spaceship, everything seems to be normal. If you had a TV that could magically link with Earth, we'd all look like ants moving around really fast. So that's the way I visualize it. So.
What would happen at time if you actually went the speed of light? Would it stop?
Yeah. Well, we don't think mass can go the speed of light, right? That's one of the...
But you could get really
close,
really
yeah,
close.
yeah. I guess so, yeah. So, oh yeah, he's trying to hand off the mic. Okay.
Just a follow up.
Oh, jeez.
I came across that our Milky Way has Sagittarius A.
Right, Sagittarius A. Yep.
Right, it's our own black hole. Congratulations, we
Yeah.
have our own.
Yeah, we have our own black hole. There's one even closer. My students were telling me something about one 1,600 light years away or something. So I looked that up.
Interesting.
Is that what you're about to talk about?
No chance.
Oh, okay. Okay.
So I'm interested in so in 2019 was when the Event Horizon Telescope did the M87.
Oh, okay. Was it 19? Okay.
It was 2019. When they compare those, what we can see clearly, Sagittarius A and M87, they're the same size relative to our space. Can you help us understand how one black hole, which is 6.5 billion times the mass of the sun, looks the same as one that's only 4.3 million times the size of the sun?
Yeah, so you're talking, which one is 87 bigger than, 87 is bigger.
Much
What was the
bigger.
numbers again? How much bigger?
87 is 6.5.
6.5.
It's more than 1,000 times larger than our Sagittarius.
Okay. Yeah. My gut feeling, the answer on that is probably our tech isn't good enough to detect the difference. To be able to see what's going on in a galaxy that far away compared to our center. Plus, the center of our galaxy is real tough to see because there's so much stuff in the way. So we're in that galactic plane that makes it real difficult to observe. So
I think one of the things about science is, you could say that it keeps changing. It's just that we keep learning more. And so I think now that we're starting to see actually, find ways to image these black holes, now we can start doing more research, based on the information we're getting from that. Any other questions here? Go.
I was thinking about the movie that came out, Interstellar. The image they had of the black hole, how it looks, you see the light from the accretion disk, I think it is.
Yeah,
it wraps around, so you have to get that dome over the top of it.
Oh, okay.
But then through the middle of it, you see it. So can you talk about that a little bit? How
I
that
didn't
happens?
I didn't see that movie.
No.
I saw.
I
came
mean,
in,
the M87 image looks kind of like that if it could be cleaned up.
Okay.
They said, yeah.
Pretty cool. I've been meaning to check it out.
It's a great movie.
Yeah. It's kind of a tearjerker, right?
It pushes the science.
Yeah. I saw somebody, he's on a bookshelf or something. I came across that. I was like, okay, I'll skip this because I want to see the rest of it. Like, I want to start it from the beginning. It looked good. Okay.
So, there's like the accretion disk, and that's like one plane across, like horizontally. But what happens if you're like 45 degrees from the accretion disk? Do you still get sucked into the black hole?
Oh yeah, because the gravity's still there. It's just you're just gonna somehow eventually get onto that disk probably, but maybe not. No, the gravity's still there. That's a good question. So, but more is along the equator. Like if you think of it as being like a planet, you know what I mean? So, what was that?
Anything else on the chat?
Oh,
Or
okay.
a couple more from the chat.
So Gary asks, is there an upper limit to the mass of a black hole before it turns into something else, or is that the end of the line?
Is there an upper? I don't know. I don't know. Upper limit? I wouldn't think so. You could keep more and more massive. I don't know. That's a good one. Yeah, the whole universe would be the upper limit, but that's what I said. We could be in one, right? Okay,
Yeah.
so go.
And then Mike asks, how long does it take a black hole to evaporate?
Well, that's the thing. It's what Penrose is saying is going to be a long time away. So it's 10 to 100, 1 times 10 to the 100 power. So we're talking 1 with 100 zeros. That's what a Google is. So you learn something new, right? You'll remember that. So that's when the universe will all start puffing away. So that's. I'm not sure on how long the actual process is.
All right. Unless there's any other questions, Roy, I want to thank you once again for your ever popular Black Holes on Black Friday. Yep.
All right, thank you.
And actually, if I could have the kids come back up here, we're going to do this experiment one more time because we have a different lens on our camera, so that the people on the live stream get a better sense of that. So,
Okay, great.
So who's going to be our black hole?
Okay.
You're going to be okay. Okay, so you go
You got
underneath.
this, Drew?
Okay, I'll do it. I turned off my mic. Oh, yeah, you try to turn it back on. Here, I'll do it. I got it turned on. Okay, here we go. So, which camera's going to shoot it? What do you got? Okay. So, anyway.
All right, we got our black hole in place.
Everyone get some marbles. Here you go. Here we go. And I'll see. I doubt this will work, but I'll give it a try. Oh, I didn't know you're still down there?
Yep. Okay.
Come on up.
Okay.
You stayed there the whole time. Oh, okay. Okay. Oh, okay. Who's down there? Okay.
All right.
You get hit with this thing. Okay, so this is pretty. This is got to be lead, right?
Yeah.
You don't want to get hit in the head with that. All right, so let's just do a few at a time, right? So again, yeah, just try to orbit. Just try to do an orbit. Okay. No, don't go the other way. So go. No, you can. So now again, I'll try the moon. So watch this. I'll try. So everyone stop for a moment. Let me try the. So here's a planet. All right. And let's try to see if I can get a moon to orbit it. So this looks like a good one. Usually I see that. Okay, here we go. You ready? Watch. Yeah, see that's kind of orbit. Let me see. Try to get it.
And for those of you who are here tonight, when you go home, go to our YouTube channel and you can see what they were doing. This is the-
Jeremy, we don't have another one?
what? That's all I have right now. I think I'll go look.
Look, see the. You can really see it. You can really see.
Projector still on.
So a planet is warping space too. You know, not just a star. So the bigger it is. So.
I can just mute it on here. So is that, yeah, it's muted already.
There you go.
Now, those that are here are actually watching our YouTube channel. So,
If you put the camera on this, will it be feedback or something?
yeah. We sucked into the video black hole.
Okay, I think my job is done. You guys can play with the marble. Here you go. Here you go. All right. Yeah, that looks good. That actually looks really. It looks a little little lopsided. I don't know if that's the camera or if it really is. Oh yeah, I have no idea if this is gonna work. Two golf balls. I don't know. Let's try. Here, let's try this. As a teacher, they say never try something like live for the first time.
Yeah, and we would ask you as you're leaving, watch your step because there's got to be marbles all over the flare.
Yeah, hold on. The fabric of time and space. Okay, here we go.
And also, for those that are here for the first time, if you'd like, we will, let's see, it's about 9 o'clock right now. At 10 minutes after, if you go meet me out in the lobby, we can do an actual tour of the observatory. I can take you out and show you a couple of our scopes. So if you'd like to do that, we'll meet in 10 minutes out in the lobby, and we'll go from there.
How many do we have on